Hello everyone, I am an AI assistant of the Earth Science Research Promotion Center. ESRPC Taiwan. Taiwan is located in East Asia, at the boundary between the Eurasian Plate and the Philippine Sea Plate. This unique geographic and tectonic setting makes Taiwan an important natural laboratory for earth science research. Our mission is to promote Taiwan's earth science research results to the international community so that more researchers and scholars can better understand the development of earth science in Taiwan and foster more international collaborations. Earth science consists of 7 major disciplines: geology, geophysics, oceanography, atmospheric science, geospatial information science and technology, disaster remediation, and sustainability science. In the following video, we will introduce the key research achievements of each discipline in Taiwan. Let's start with oceanography now.
Hi, I am Oceanography. Seagrass meadows are recognized as scalable marine carbon dioxide removal (CDR) pathways. Beyond organic carbon sequestration, sedimentary alkalinity production enhances the ocean's capacity to store CO2. Our results show that seagrass meadows established on reef-derived, high organic carbon (OC) sediments generate alkalinity fluxes up to 2 orders of magnitude greater than low OC environments. This enhanced production is associated with significantly lower seawater PCO2, indicating increased potential for sustained air sea CO2 uptake. These findings position high OC, carbonate-rich seagrass systems as natural analogs of ocean alkalinity enhancement and high-efficiency CDR hotspots. Policy-wise, integrating sediment biogeochemical context into blue carbon frameworks is essential. Prioritizing the protection and restoration of seagrass in these settings can significantly amplify climate mitigation and should be explicitly incorporated into national carbon accounting and marine CDR. Next up is atmospheric science. Bye-bye. See you next time.
Hi, I am an atmospheric science. Pioneering collaborative atmospheric observations in Taiwan, the evolution of cable 2024 and FOWS 2025. The NSTC's Atmospheric Science Division launched a collaborative observation series in 2024 to address the scarcity of high-resolution atmospheric boundary layer (ABL) data, crucial for understanding extreme weather. Phase 1, Cable 2024. Conducted in Chiayi August 11th to September 3rd, this phase used Doppler lidars and microwave radiometers to capture preconvection conditions. It successfully recorded 9 precipitation events using advanced data assimilation (WISDOM/TPTRS). Phase 2, Cable FOWS 2025. Expanded July 17th to August 14th to integrate space science, studying interactions between solar activity, gravity waves, and lightning. Key achievements include: scale increased from 10 to 23 instruments across 13+ institutions. Milestone, detailed observation of the 0728 extreme rainfall event using TEMA mobile radars. Impact, engaged 100+ students, fostering future experts while enhancing regional disaster prevention and early warning systems. Next up is disaster remediation. Bye-bye.
Now, it's my turn to introduce the disaster remediation. This research investigates sediment disasters and adaptation strategies in the Wu River Basin under climate change. The key findings are summarized below. Advanced monitoring. Time series INSAR detected riverbed deformations of +5 liminant year. Additionally, a new bridge pier scour monitoring method was developed using triaxial accelerometers, resulting in a dimensionless formula for scour depth. Modeling and morphology, HAC, HMS, and SRH 2D models simulated sediment transport under extreme weather, which was found to significantly alter river meandering and sandbar formation. Ecology and risk assessment. Habitat surveys for the endangered Aphaeocyprus linnae identified critical flow velocity and depth factors for restoration. For urban safety, a 3-variable copula model, rainfall, duration, and river stages, was coupled with levee effect theory to assess compound flooding in the Fosse River. These integrated efforts provide a robust framework for watershed management and early warning systems. Next up is sustainability science. It's time to get off work. Haha.
Hi, it's time for sustainability science. Now, let's bring your attention to an example of the solution-oriented, stakeholder-engaged, and transdisciplinary sustainability science research. Along Taiwan's Zhonghua coast, our research tracks a landscape in flux. Our remote sensing data reveals 2 critical shifts. Changing sandbar migrations are disrupting traditional oyster farming, while expanding mangroves are shrinking the bare mudflats essential for native crab diversity. Simultaneously, we found that while new coastal skywalks boost ecotourism, they inadvertently create fragmented local networks and increase environmental stress. But research outcomes must do more than document decline. By interviewing local residents, we uncovered the human side of these ecological pressures. This pushed us to bridge the gap. We are now integrating community observations directly into our scientific monitoring. By answering local needs with rigorous data, we are turning academic findings into tools for stewardship. Together, we are building a more resilient social-ecological future for the Zhonghua coast, ensuring that our research serves the people who live and work here. Bye-bye. Next up is Geospatial Information Science and Technology.
Geospatial Information Science and Technology, GIST. Taiwan's path to sustainability. Taiwan's unique location at the boundary of the Eurasian and Philippine sea plates makes it a natural laboratory for Earth science. Geospatial Information Science and Technology, GIST, integrates GIS, remote sensing, surveying, spatial databases, and digital twin technologies to link scientific knowledge with real-world decision-making. GIST enables the integration of terrain, climate, building, and solar data to support sustainable energy planning. It combines satellite imagery with geological and rainfall information to assess landslide risks and slope stability. Digital twin modeling allows virtual testing of strategies before applying them in reality, bridging research and policy. Focused on quality, performance, and efficiency, GIST advances research across environmental science, geology, civil engineering, transportation, and public health. By integrating spatial data, analytics, and collaboration, it provides practical solutions for complex societal challenges. As Taiwan builds a digital nation and smart island, GIST strengthens international collaboration, promotes Earth system research, and supports sustainable development for a more resilient and innovative future. Next up is Geophysics and Geology. Bye-bye, see you next time.
Hi, I am Geology and Geophysics. The NSTC Geology and Geophysics discipline focuses on understanding how the Earth works and how these processes affect human society and the natural environment. Most of our research is centered on Taiwan, a region with active plate collision, frequent earthquakes, rapid erosion, and complex fault systems, making it an ideal natural laboratory for Earth science. This year, the first research highlight comes from Professor Chen Fengyu's team at National Tsinghua University, published in Science of the Total Environment. In this study, they used the Southern Geochemical Platform to analyze lithium isotopes, deltally, in groundwater and river water from the Gaoping and Choshui rivers. It is one of the first systematic applications of deltally to Taiwan's small mountainous rivers, providing a sensitive tracer for silicate weathering and water-rock interaction time. The study shows that seasonal changes and extreme rainfall events, such as typhoons, strongly affect chemical weathering. During storms, rapid water flow shortens water-rock reaction time, pushing the system into a kinetically limited weathering state. The research also identifies soil pore water as an important hidden source of dissolved weathering products, especially during dry season river discharge. By combining deltally with senior isotopes, chemical weathering rates, physical erosion rates, and isotope fractionation models, the study provides a more quantitative understanding of weathering efficiency, solute sources, and mineral controls in rapidly eroding rivers of western Taiwan. The second highlight is a breakthrough in high-precision geochronology from National Taiwan Normal University, led by Meng Wanya. This work was published in the 2024 Elsevier Book Methods and Applications of Geochronology. The NTNU-affiliated research demonstrated a high-level capacity for advanced geochronology through an integrated methodology. This approach combines in situ 40AR/39AR laser probe dating for high spatial resolution, intragrainage patterns with detailed microstructural analysis via scanning electron microscopy. Furthermore, the capacity includes complex numerical diffusion modeling using the DIFARC program to quantify the effects of strain and reconstruct the precise initiation and duration of deformation events. This collective expertise allows researchers to move beyond bulk mineral dating to directly link age heterogeneity to specific microscale deformation mechanisms within complex geological structures. The third highlight focuses on the March 28, 2025 MW 7.7 Myanmar earthquake along the Sagang Fault, led by Professor Yuang's team at National Taiwan University and published in Nature Communications. Using ESRPC and optical satellite imagery, the researchers reconstructed nearly 500 kilometers of surface rupture and fault slip distribution. The results show an unusually sharp and continuous rupture, with most of the slip reaching directly to the surface and almost no shallow slip deficit. This means the rupture was highly efficient, with very limited off-fault deformation. The earthquake also re-ruptured segments that had broken in 1929, 1930, and 1956, supporting the idea that mature strike-slip faults can rupture repeatedly in a predictable way. These findings provide important insights for global seismic hazard assessment. Now, let's bring your attention to the MIDAS project, Milun Fault Drilling and All-Inclusive Sensing, which drilled directly into an active fault in Hualien, eastern Taiwan. In the MIDAS project, researchers completed a 700-meter scientific borehole across the Milun Fault and installed optical fiber cables directly inside the active fault zone. This is highly unique because it allows us to observe fault behavior from within the fault core itself, rather than only from surface rupture or seismic waves recorded at the surface. This leads to the fourth highlight, deep fault monitoring of the Milun Fault in Hualien, published in Communications, Earth and Environment. Using distributed optical fiber sensing in a borehole across the fault, Guofan Ma's team directly measured strain changes during the 2024 MW 7.4 Hualien earthquake. They found that the narrow fault core, located about 520 to 540 meters deep, produced much stronger strain signals than the surrounding rocks. This amplification is caused by weak fault gouge trap between stronger host rocks, creating strong rigidity contrast. The fault zone acts not only as the place where earthquakes rupture, but also as a natural amplifier of seismic energy that strongly controls future rupture behavior and hazard. In summary, these studies show how geology and geophysics transform Taiwan's complex earth processes into scientific insight with global relevance. By integrating observations from minerals, rivers, faults, and earthquakes, the discipline advances both fundamental earth science and society-focused understanding of natural hazards. We are all finished. Thank you for watching. See you next time.
These are recent research achievements in Taiwan. If you are interested in collaboration, please scan the QR code.